No problem. Okay, yeah, so I'm here today, just to reiterate really quickly, giving a talk on dark matter and complex stars and galactic structure. I'm a professor at Queen's University, but I also have appointments at Perimeter Institute, and I'm a member of a Canadian organization called the Arthur B. McDonald Canadian Astroparticle Physics Research Institute, or just the McDonald Institute for short. So we'll be addressing three main topics today, and I understand that a lot of us are from a particle background, and I'm talking a lot about astrophysics today. So please feel emboldened to ask me any questions you want about what I'm talking about, because some of it is very far from what we're normally used to talking about. And hopefully I'll have a good answer if you have a nice, good basic question, or even if you have any question, hopefully I'll have a good answer. So dark matter heating neutron stars will be the first topic. And this applies to a lot of dark matter models and is an interesting, somewhat near future, but as I'll show, maybe not too far future sort of way to look for dark matter. The second topic I'll talk about is how asymmetric dark matter, which is a broad class of models, but the class of models we're talking about here fall into a certain mass range that I'll go over, and how these can cause neutron stars to implode and turn into black holes. And then I'll point out some interesting connections to missing pulsars and possibly a little bit on fast radio bursts. And lastly, I'll talk about dark matter in a different kind of compact star, a white dwarf. And here I'll talk about dark matter causing white dwarfs to explode. The same kinds of asymmetric dark matter. Also, I'll mention composite dark matter and how that can make white dwarfs explode. And just as with the asymmetric dark matter causing neutron stars to implode, there will be both bounds I can set on this and some interesting signatures to look for. One will be type 1a supernova and sort of patterns that they can have. And the last interesting thing that you should see on the archive in the next week will be ties between dark matter that makes white dwarfs explode and galactic structure. Okay. So let's get started with dark matter that heats up neutron stars. So I like to think about neutron stars as nature's dark matter accelerators, because literally that's what they are. So if you think about dark matter moving around in the galactic halo nearby us, it'll be moving at a speed of about 10 to the minus 3 times the speed of light. But neutron stars will accelerate it up to a speed of 0.7 times the speed of light. Neutron stars are dense, so they accept a very large dark matter flux. You can think about it as a detector with a fiducial mass of around 10 to the 57 GeV, where it has about 10 neutrons for 1 proton and 1 electron. So protons and electrons are inside the neutron star due to its high chemical potential. And if you want to think about the flux of dark matter through the neutron star in terms of a terrestrial unit, about 100 grams of dark matter flows through a neutron star by Earth every second. Lastly, if you want to think about what it takes for dark matter to scatter with the star, for dark matter to scatter once as it moves through the star, it needs a cross-section with nucleons of about 10 to the minus 45 centimeters squared. So the basic idea of dark matter kinetic and annihilation heating of neutron stars is very simple, which is part of what makes it powerful. And that's that dark matter is sped up. And so if it hits the neutron star, it will be gravitationally captured if it satisfies certain conditions. And so it'll be on an orbit around the neutron star and it'll scatter over and over. And the process of scattering over and over, it'll heat up the neutron star to a temperature around 1750 Kelvin if the neutron star is heated just by kinetic energy of the dark matter. But if the dark matter also annihilates, it can heat up the neutron star all the way to 2500 Kelvin. And I can compare that with what a neutron star's temperature would be at late times here being really any time after tens of millions of years would be suitable for making this kind of measurement. And what I find is that the temperature of a neutron star should be well below what dark matter heats it up to. So I can ask, what sort of sensitivity could I get from dark matter if I were able to look at an isolated neutron star and either see or not see it glowing at a temperature of 1750 Kelvin, or even more futuristically, maybe 1000 Kelvin. And what I have here are some very simplified but relatively accurate sensitivity curves in terms of the dark matter nucleon scattering cross-section and mass that you're used to looking at. And this sort of a dark matter probe would extend up to extremely high dark matter masses. That's my cat, Paprika. I'll just introduce her really quick so you can say hi, and then I'll go back to the talk. All right, so So this goes up to actually very high dark matter masses. I can talk about that if you want later. But in principle, I can think about measuring neutron star temperatures down to 100 Kelvin, although in practice, even getting to this curve here would be a futuristic endeavor that would require an enormous amount of telescope time on a 30-meter class telescope. Before I show you a little bit of particulars of what that kind of search would require, let me show you a very long list of models people have considered in the last 8 years since my colleagues and I started writing about this, that you could look for using dark matter kinetic heating or dark matter annihilation heating of neutron stars. I should also definitely mention and emphasize.
May I chime in?
Yes. Yes, please.
So from literature, it seems that the magnetosphere of a neutron star is roughly on average 6,000 kelvins. That could be much larger than the kinetic heating of dark matter. So I'm wondering how this would affect your results, or have you taken this into consideration?
So I'll show you our discussion of alternate heating mechanisms, or I'll tell you which references to look at there. So when you say the magnetosphere is 6,000 Kelvin, we'd have to look at which reference you're looking at. There are a number of references that look at what's sometimes called a rotochemical and sometimes called like a magnetospheric heating of neutron stars. So depending on which class of neutron star you're talking about, if you're talking about a very young magnetar, then that's probably not the kind of neutron star we're thinking of here. But if we're thinking about transferring the magnetic field energy to the neutron star, a very old neutron star, the sort of processes where that would occur, it should have already sort of worn itself out, so to speak. There are some very recent proposals for how a certain kind of rotochemical heating could heat up neutron stars at late stages. But what all of these sorts of proposals have in common is that none of them have been measured. And in fact, there's very little evidence that there should be a heating process that competes with this, that's internal to the neutron star based on observations of the younger neutron stars we've seen. However, I can't, of course, completely rule this out because we're operating with something where we haven't measured neutron stars down below a certain temperature. But I would just emphasize, if you're looking at a particular class of neutron stars or pulsars with extremely high magnetic fields, that's not the kind of neutron star we're talking about here. The kind of target we're talking about is one where the magnetic field is going to be fairly low. It's not going to be magnetar strength. It's going to be something like a second period pulsar that's 100 million years or older. But yeah, to get into the details of that, we'd have to have a longer conversation and look at which references exactly we're talking about. But yes, thank you. Very nice question.
Okay, thanks. I think like accretion or other mechanisms would affect the temperature of the neutron star atmosphere a lot. And I'm just wondering, what is the fraction of the neutron stars that are very, very cold, so that we could really see the effects of dark matter magnetic heating. But anyway, this is probably a separate question that involves.
Oh, that is a separate question, but let me talk about that. I'll come back to that in like 2 slides. So just give me 2 slides, and then I'll come back to the question of how many of these are isolated. These are very good neutron star questions. All right, so yeah, so the sensitivity to all these models that I have up on this slide essentially comes from the fact that neutron stars have all these fun properties, like, you know, they have a muon fraction. You're going to boost this dark matter to an extremely high speed, so all sorts of dark matter that normally gets away from your direct detection experiments by either having inelastic transitions you can't see, or having some sort of weird loop level interaction, which secretly has actually a momentum suppression in it. All those sorts of models end up being quite easy to see using these sorts of neutron star methods, and that's fun. Let's talk about what we've actually seen with neutron stars, and then we'll get more into Ning-Yang's line of questioning, which is a really good one. So if I look at the temperature of the neutron stars here in Kelvin, and I look at the age of the neutron stars in years, we can see what I'm saying playing out in these model cooling curves shown here, which is that after 10 million years or so, cooling curve models as they exist in literature will tell you that the neutron star should cool extremely rapidly, well below the temperatures that we want to see them at. But what you'll notice here is all these temperatures are at like 10 to the 5 Kelvin, and what I was quoting before is more at 10 to the 3 Kelvin. And so, this is the question, what is actually the coldest neutron star seen? It's actually not shown on this plot. And it actually wasn't around when we first started working on this. The coldest neutron star seen ever is pulsar J2-144 3933. It is the sort of class of pulsar that is of the kind that we'd want to go search for if we were going to do this measurement, although it isn't quite perfect. It's about of order 300 parsecs away. And using an extended campaign of Hubble telescope time, not too long though, Guil and all were able to put a bound on the temperature of this neutron star of less than about 3 times 10 to the 4 Kelvin, where depending on how you want to do the significance, it might be more like 4. So that's not cold enough to set a bound on local non-subhalo dark matter, and I'll get into what a subhalo dark matter model can do to this neutron star, because that'll heat them to like 1750 Kelvin. But it just shows you that this sort of basic procedure has been done. We just need to do it in order of magnitude better in temperature, which means 4 orders of magnitude better in luminosity. Now, when we ask what kinds of targets we would actually want to look for to do this measurement, this brings us to Ningyang's question. And I don't have my giant pulsar plot because I was expecting not to talk to people who had lots of questions about pulsars today, but that's okay. So the basic answer to the question, what kinds of neutron stars should give us good targets? The answer to that, and it might sound like I'm overselling, so I'll try to qualify it after I say this, is most of the neutron stars in the dark matter halo, or sorry, in the galactic halo around us, should be good neutron stars for doing this measurement. Why is that? Most of the neutron stars around us are older, much older actually than 1 billion years. And most of them are not going to be millisecond pulsars, so very fast spinning pulsars that maybe have sort of those rotochemical processes which could heat them back up potentially, although even then, most of those rotochemical heating mechanisms should themselves damp out after something like 10 million years by the people, well, according to the people who study them, but who knows really. And so the kind of pulsars we're looking at are something like around second period, or pulsars that pulse around every second, somewhere within the 100 parsec region away from Earth, and with a characteristic age that's older than 10 million years. Now, a characteristic age is the age you can infer for a pulsar by looking at its pulse period and dividing that by its spin down rate. Don't worry about it too much, but basically you can use the pulsar's pulsations as a kind of clock to tell you how long roughly it's been spinning. And that can tell you, you're looking at an old pulsar. So for instance, if I just go to the ATNF pulsar database and I say, which pulsars have the sort of characteristics I'm talking about, I would come up with this list. However, this list comes with a big asterisk next to it. And I'm actually doing a big project right now, or I should say my grad student, Narani Tyagi, is doing a big project where she's studying all these nearby pulsars, not just these, but everyone within about like 500 parsecs. And in collaboration with a pulsar astronomer named Li-Jing Xiao, we're coming up with a good set of candidate pulsars to do follow-on observations of in radio to get really good distance estimates, because for reasons I won't go into today, these distance estimates are a little bit shaky. And hopefully they'll be at lower temperatures. Now, if they, for some reason, have some sort of internal process or something else that means that they don't have the temperatures we're talking about, then that's something else we'd have to talk about. But just to address Ningyang's other few points, without my handy pulsar heating slides, which I'd have to scroll down for, and I'm not going to do right now. There's a question of accretion of the ISM onto the nearby pulsars and whether that would heat up the pulsars to a higher temperature than this 3000 Kelvin. So the ISM around the Earth, it turns out, is underdense relative to what you would expect for the galactic ISM. So the galactic ISM would compete with, but in most regions actually heat up a neutron star below the temperature that we're looking at, if you just naively assumed that the ISM accreted as a collisionless particle onto the neutron star. Now, you don't necessarily need to assume the ISM accretes collisionlessly onto the neutron star, because you can assume that it has some sort of fluid accretion onto the neutron star. That brings us into an entirely separate discussion where historically it's essentially been shown that fluid accretion vastly overpredicts ISM accretion onto neutron stars. And one of the main pieces of evidence for that is that we don't see thousands and thousands of old neutron stars in giant molecular clouds giving off X-rays like they would if they could accrete baryonic matter like a fluid. And so most models for how ISM accretion on pulsars actually occurs have to incorporate some amount of magnetic deflection from the pulsar in order just to match the non-observation of all these X-rays. And that already puts the fluid accretion sort of level of accretion on shaky ground by a few orders of magnitude at least, so that you shouldn't assume that fluid accretion works within like 2 or maybe even 3 orders of magnitude. And so then what the actual correct baryonic accretion rate onto old neutron stars that are just sort of floating out in the halo that we don't really know much about because they aren't necessarily pulsating that much, is something that's kind of an open question. Okay, so I'll stop talking about that, but if there are more questions, definitely ask me more, and happy to talk with anyone, especially Ning Yang, about this offline at the end. All right, so if we move on for the moment to ask if we don't want to wait for the future and sort of a futuristic measurement of a neutron star at a low temperature with all the fun that's going to involve in order to get that done, what can we do today when it comes to neutron stars and dark sectors? And it turns out that we can actually still say something quite interesting about neutron stars and their interactions with dark matter in a certain limit of our dark matter models. So actually, I just talked about there's a difference between collisionless accretion and collisional or fluid/bondy accretion onto our neutron stars. So collisionless accretion will have a collection radius around the neutron star that goes roughly like the escape velocity of the neutron star, which remember is 0.7 c, divided by the velocity of dark matter in the halo, which is around 10 to the minus 3 c. So this will give you essentially an effective collection radius that's 1,000 times larger than the radius of the neutron star. Bondy accretion, very roughly speaking, gives you something that's 3 orders of magnitude greater, or a factor of V escape over V dark matter greater. This Z factor just relates to the blue shift of the particles as they fall onto the star. Don't worry about that. It's just a very small correction factor related to GR effects for accretion onto the star. And so, yes, please.
So what do you mean here with collisionless and collisional?
So collisionless means I can treat the motion of the dark matter around the neutron star as occurring just like every single dark matter particle is a free particle. So that's probably what we think in our heads.
You're talking about
dark matter falling onto a
You're talking about self-interaction?
Yeah. And then this is the limit of extreme self-interactions where it's not even a little self-interacting, it's a fluid. It's like it's a fluid with like a standard equation of state. And so it's like a gas that actually reacts to the motion of the neutron star through the halo. And so it creates a kind of wake that increases collection. And to actually do this calculation correctly, you have to do boundary condition matching of a spherical body inside of a fluid in order to figure out how much fluid flow would go onto that body.
Thank you.
Good question. Yeah, of course. Thank you. So you can think of this, as collisionless, and this as like extremely collisional self-interacting dark matter. And so normally you'd say, well, we can't have extremely collisional self-interacting dark matter, but the context that we thought about this in is what if dark matter existed in sort of compact subhalos or some sort of spherical region of some size RSH and some mass M, such that it essentially only exists in those regions, or just a very small amount exists outside of it. And so those regions have to pass through either a neutron star or they have to pass through Earth in order for us to detect dark matter or heat up the neutron star. And I'll talk about Earth and what bounds we can set on that kind of dark matter using Earth measurements in a second. But if I just think about neutron stars, then I can think about two regimes for heating the neutron stars. One is where the halos pass through the neutron stars fast enough that it keeps them at a steady state temperature. And one is where it passes through them rarely, so it just heats them up in periodic succession. So next, I'm going to have to show you the most complicated plot of my talk, because it's a four-dimensional plot.
Sorry, can I ask a question?
Yeah. Yes,
So
please.
this is because of dynamical heating of neutron star with the dark matter, hello, or some other?
Yes, so here we've just assumed kinetic heating of the dark matter, but there are these subhalos that pass through the neutron stars and they kinetically heat them up. Yeah.
Okay. Thank you.
Of course, thank you.
Oh, related question. So in
Yeah.
vaccines, could these main sequence stars or some other stellar black holes dynamically heat the neutron star to a higher temperature, and how large that effect would be?
Dynamic heating we'd have to talk about, and that's not a calculation we did. What was the other kind? Dynamic heating of primordial black holes, I'm not sure about. I think you mean like if the dynamic heating occurs by the black hole passing nearby enough to them that they sort of have a tidal effect on the neutron star?
Well, as long as we have some kind of compact star that passes by the neutron star, we would have this kind of dynamical heating, right?
Oh, okay. So from what I'm hearing you say now, it sounds like you're talking about like heating up the neutron stars in the sense that you can think about stellar temperatures as being like what the kinetic energy of the stars are from things passing by them and sort of shifting their velocity distributions. And here, yeah, that wouldn't be the kind of heating we're talking about because we have to heat the neutron stars directly. But I guess what you're saying is, would these subhalos have some sort of effect that's just gravitational that we could use to exclude them? And I'll definitely show you what part of the plot is excluded based on those considerations.
Well, I just mean like if we have some stellar mass black hole, which probably comes from neutron star or some supernova explosion, and then that passes by this kind of neutron star, or it could be primordial black holes. In that case, would that affect the neutron star temperature, and would that affect the previous constraint that you have placed using neutron star temperature?
Okay, so let's look at the constraint for neutron star temperatures in a moment. So for solar mass black holes, even if they were at the dark matter, at the density of dark matter, no, the collision time would be between any given neutron star and the black hole would be many orders of magnitude older than the age of the universe. But if you had a bunch of primordial black holes that are of much smaller mass, 10 to the minus 14 solar masses or smaller would be the range where I think it certainly could work. Then yeah, those black holes, you'd have to calculate whether they're captured, and those could dynamically heat up the neutron star. But you need to think about a low enough mass that the interaction between those primordial black holes and the neutron star would occur frequently enough that you could see. But yeah, you could definitely do that for the lower mass primordial black holes. Yeah. Yeah, and then let me answer this gravitational question. So if the radius of the subhalo and the mass of the subhalo, which is shown here in this upper plot, fit into a certain region where the object is compact enough, then you can actually use microlensing surveys or brightening of stars in wide field surveys to set bounds on whether that can even exist, and that's shown in the gray here. So yeah, this is showing you these subhalos, and for those subhalos, it's showing you certain regions in the subhalo radius versus mass parameter space where you can exclude certain dark matter cross sections shown here for the dark matter inside that subhalo based on a few terrestrial observations. One is the dark matter bound on cosmic ray boosted dark matter, because it turns out that cosmic ray boosted dark matter will still be boosted in these subhalos around the Earth, wherever they are. And so that flux will still come to Earth. And so I can set a bound anyway on subhalos based on the cosmic ray boosts that dark matter would get from cosmic rays and what that would look like at detectors on Earth. And then in this brown region here, I would be able to say, hey, there's this measurement made using ancient mica, which is one of the measurements actually Ning-Yang and I have made on our plots in years past. And that measurement was valid over a 500 million year time scale. And so those subhalos, even though they would pass through the Earth very rarely, would have shown up in that ancient mica that people looked at for nuclear scattering. But then essentially the rest of the normal dark matter parameter space is unconstrained in the case that dark matter is on these subhalos, because the dark matter doesn't necessarily pass through the Earth in a year or 10 years or even a million years.
So I have one more question here. Sorry.
Yeah. Of course.
Is it really possible that dark matter is all in subhalos? I mean, according to the normal hierarchical formation history of dark matter structure, it seems that you will form these small halos which then combine into large halos, but there will always be a significant amount of dark matter that is not in subhalos. And even if these dark matters are initially in subhalos, then due to various tidal disruption effects, a large fraction of these halos, of these small enough halos, will be disrupted, or at least the outer part of the subhalos will be disrupted.
Yeah. So actually that the question you're asking is a great one. So you're saying if dark matter is like matter around us and it forms sort of the same sort of structures that we see in galaxies around us, then we shouldn't expect that all of it ends up in those structures.
Right.
And B,
even if we only consider tidal disruption. But actually, if we consider the whole formation history, there should be a significant amount of dark matter that is not in subhalos.
So my only answer to that is I think you might be able to construct dark sectors that do indeed look like this, but it requires a kind of early universe cosmology that people are just, and by just I mean just in the last few years, getting into. And it's an early universe cosmology where there's dissipation in your dark matter sector that occurs a long time before BBM. So you have essentially hierarchical formation of some sort of these, dark halo objects or dark compact objects through dissipative processes in the very early universe. And I should, let you know, full disclosure, I'm working on these models right now. The reason, and there are ways you could model build so that the dark matter outside of those collapse structures that form in the very early universe goes away after those collapse structures form. And additionally, I think there's parameter space where in that case, all your dark matter that you end up with is in the collapse structures. But I agree with you. This is a very, very specific model, which isn't going to be fulfilled by most dark matter models. And when people have previously thought about dark matter substructure, they've really thought about the sort of dark matter that would form substructure in sort of the hierarchical fashion that you're talking about, Ning-Yang, where you have something like a matter-dominated expansion in your early universe that takes your normal dark matter power spectrum fluctuations and just sort of causes them to increase a bit. So you'd form subhalos, but they'd be like NFW subhalos that are just a bit denser than what dark matter subhalos we expect. And in that case, it's not going to look like this at all. So partly the reason that we're doing this is just to show that there is a sensitivity to a somewhat exotic or new or perhaps unexplored dark matter parameter space. But I think you're right. It's a very special parameter space.
I see.
Just to jump sort of to the upshot. So if I think about these subhalos as having Bondi accretion for neutron stars that move through them, then it turns out that there is a window of parameter space here shown in orange, where that old cold neutron star I talked about earlier, and by cold in this case, I guess we mean 40,000 Kelvin or cooler. That neutron star would have been heated up by subhalos that are of a size with a radius here and a mass here shown in this orange region, and with any dark matter scattering cross section above this black line shown here. And so that's a kind of fun result because it shows you that neutron star heating by an admittedly quite novel or exotic dark sector is something we can already rule out based on the coldest known neutron stars. That actually brings me to the end of this section. If you want to learn more about like alternate heating mechanisms, standard model and otherwise, I can give you this paper as one example, although as more papers come out on this, you'll be able to find many papers on things that aren't dark matter that could be heating up the neutron stars at late times, and why that may not be a competing background to the dark matter. And yeah, there's a lot of stuff lying around right now, which is great. Okay, so that brings me to the end of dark matter heating neutron stars. Any questions that I didn't get to? Okay, thank you so much for all the good questions so far. And so that leaves me with my last two topics. The first one will be asymmetric dark matter that can cause neutron stars to implode. So we're going to turn to dark matter that is a particle or an antiparticle under some symmetry. The main reason we'll talk about asymmetric dark matter here is so that it doesn't annihilate inside the neutron star, but it builds up and collects in mass over time. So any dark matter model you can think of that wouldn't annihilate inside the neutron star can really fit into this sort of search that I'm going to talk about now. But this isn't necessarily the heating search, and it's also something that's already been done. So there are some really strong constraints on asymmetric dark matter from neutron stars. And there are some connections you can think about to missing pulsars. So let's just review again, dark matter just collecting onto the neutron star. So dark matter will be captured and it'll end up on a wide orbit, and then it'll scatter more and more with the neutron star and end up on a tighter and tighter orbit inside the neutron star. And there are different so-called thermalization times associated with this. But after that occurs enough, it'll be in sort of a tight ball at the center of the neutron star, with a temperature determined by the neutron star temperature because it's been scattering and rescattering the neutron star. And it'll actually have a fun harmonic oscillator potential because the neutron star is roughly of constant density at the center. And so a virial sort of argument will show you that the dark matter sort of will wobble around in this central harmonic oscillator potential inside the neutron star. The radius at which it collects for the sort of very heavy dark matter we're going to think about, and a reasonable, even early time neutron star temperature. So for a late time neutron star temperature, it would be an even smaller radius by a factor of an order of magnitude. The radius is extremely small. It's like a millimeter for PV mass dark matter. So if I collect dark matter and I keep collecting dark matter, it turns out I can collect enough dark matter that the density of the dark matter in this central small region comes to exceed the density of the neutron star material around it. And you can do a very careful Jeans mass analysis there and convince yourself that for most dark matter models, it'll reach a point where it does collapse under its own weight, and it can continue collapsing and shedding gravitational potential energy by scattering with the neutron star, and it can form a small black hole. Now, before I talk about it forming a small black hole, let's talk about what kinds of dark matter actually would do this. You can't actually use GeV mass asymmetric dark fermions. And that's because degeneracy pressure stabilizes up to a solar mass of dark matter. We know this because the neutron star itself is a solar mass of fermions with GeV masses that are stabilized by neutron degeneracy pressure. And it turns out that you're only going to collect about up to 10 to the minus 12 solar masses of dark matter inside your neutron star, even for extremely dense dark matter environments at the center of galaxies. And so we can't collect enough dark matter to form a solar mass black hole inside the neutron star, essentially. What you can do is think about bosonic dark matter, but there are a lot of model constraints on that. We can talk about that offline and why you have to carefully consider how the bosonic dark matter couples to itself before you conclude that it doesn't have Fermi degeneracy pressure, so it can collapse. But what you can also consider is just really heavy fermionic or bosonic asymmetric dark matter. For the bosons, then you don't have to worry about what their self-coupling is. It turns out they'll follow much the same Chandrasekhar mass condition, and you can plug in the numbers here and you'll find that for PV mass dark matter, you will start to be able to create small black holes that are above their Chandrasekhar mass within billion-year timescales. And so once you've now built up enough dark matter that it can collapse under its own weight and it's above its Chandrasekhar mass, you can form a black hole. And I should say here, I gave you a very simplified treatment of all steps along the way. Here, what I'm showing you is that you then have to do another step, which is to calculate whether that black hole is big enough that it will efficiently accrete baryons around it through a Bondi accretion process in the end, although with a fluid speed for the neutron star that's extremely high. It's like between 0.1 and 0.3 times the speed of light. So this is just a Bondi accretion term. But you also have to compute Hawking radiation, and whether Hawking radiation actually would cause the black hole to evaporate away faster than it can accrete neutrons. And one refinement to this calculation I made back in 2013 when I was a grad student is I put on a third term, which ends up being relevant, which is the amount of dark matter you're accumulating onto the black hole can change whether it's going to evaporate or whether it's going to continue growing. It's actually a very substantial part of this calculation. If you're accreting dark matter at anywhere near the maximal rate that you can accrete dark matter onto the neutron star. And then other people have considered a lot of other refinements to this. Like you can think about whether the Hawking radiation is free to freely radiate inside a neutron star, or whether there's a certain amount of polyblocking. So the point is, at every step of the way, there are refinements to all these processes. But if you do a simple calculation, you can convince yourself that above a certain mass, the neutron star will have a tiny black hole in it. That definitely will grow and cause the neutron star to convert into a black hole. And you can say, well, we've seen neutron stars around us in the galactic halo, and the galactic halo has a certain dark matter density. And so what bound can I place on dark matter just based on this sort of principle? And this is the bound you can already place on dark matter based on asymmetric dark matter not forming a black hole inside of it. Here, you can consider either bosonic or fermionic dark matter. Without anything really special, the bosons can have an order 1 self-coupling, and that's fine. And this shows you roughly the parameter space that you can already set a limit on, and that's sort of the current direct detection limit. So you can see we're at cross sections that are well below that direct detection limit, but we're also at quite high masses, and this is related to the fact that you need the Chandrasekhar mass of the object to be much smaller than a solar mass. So at the highest masses, you end up forming black holes because the dark matter collapses earlier because it's in a tighter ball inside of the neutron star. And these black holes are too small and they actually do evaporate away. And then at lower dark matter masses, the black hole never forms. And so an old Milky Way pulsar that we selected from all the pulsars because it had a white dwarf next to it that had an age that was bang on with the characteristic age of the pulsar, so we're very sure about its age, or as sure as we could be, is what was used to set this bound. And that's corroborated by other pulsar ages as well. So this is really based on one Milky Way pulsar, but you can find other Milky Way pulsars that are as old as that one easily. That one's about 3.5 billion years old. There are many pulsars that people think are much older than that.
Sorry,
Okay, but they're, yeah.
Sorry, can I ask a question?
Yeah.
So in previous slide, you told about this dark matter thermalizes. So I'm curious
Yes.
about that. When dark matter can thermalize, then how, I mean, in the lifetime of neutron star where there is a possibility of thermalization, and also if there is
Yes.
a possibility, then how it can be related to the black hole formation?
Okay, so the thermalization process is the process by which it sort of eventually reaches the temperature of the neutron star through repeated scattering. At sort of the limit of the parameter space we're talking about, you can think about dark matter that scatters once as it passes through the neutron star.
Mm-hmm.
And the sort of speeds you can think about for that happening are like millisecond timescales. And so that already gives you a sense of how many times even per second when it's first captured, it's going to scatter at the neutron star, which is something like 1,000 times per second. And so the thermalization actually for the stage up to here is extremely fast. Whether late time thermalization can happen efficiently or not is actually a very deep question. But for the parameter space I'm showing you here, it happens on time scales less than, I believe, a year. Come to me afterwards if you want to. There's some actually great papers on this and still good papers being written. Because accurately computing the low energy thermalization of the dark matter and the neutron star means you have to model the neutron star fluid and polyblocking of the scattering process appropriately. And that's not necessarily a trivial calculation, although it's been done by a few groups now, and there's good agreement on what the
Okay, one more question. This, when this dark matter try to thermalize, when you just interact with the neutron star medium, so every time its radius start decreasing, right? Because of the energy, I think, transferred to neutron star.
So I don't think I don't think the radius of the neutron star would decrease very much.
Sorry, not neutron star. This a radius, I think, effective radius of interaction between neutron star and dark matter.
Oh,
so
so that decreases until it reaches an equilibrium value at this thermalization radius I showed. Because once the dark matter reaches the same temperature as the neutron star, it'll essentially have a fixed orbit at a certain radius, because it won't cool down or heat up beyond that neutron star temperature. But then the point is, once you put enough dark matter into that radius, eventually it can be unstable to collapse under its own weight. And then it can start collapsing and transferring more energy to the neutron star during the process of that collapse.
Okay, so here you are considering that all the energy of the dark matter, I mean, this goes directly to the neutron star part here, right? And then
so the
quantity of dark matter start decreasing. So isn't it like a possibility of the gravitational wave radiation because of energy loss? Or you assume total energy loss is going?
That's a very good question. Yeah, there is actually, even though there's a lore that there's no gravitational radiation associated with spherical objects or spherical collapses. The sort of dynamics of the actual collapse of the dark matter and the formation of a small black hole is actually something that some authors have explored, whether they're high frequency gravitational signatures you'd associate with that, and whether you could look for that. I'd have to dig up the reference. It was one paper from like 2015 or 16. But
because first approximation, we can't consider dark matter halo as a totally spherical object.
That's totally what? Sorry.
So I'm saying in first approximation, in the general approximation, we can't assume a dark matter halo to be totally spherical object. I mean, it may be some deformation like ellipticity and all those things. So overall system may be not spherical symmetric. And I think, I may not know, maybe you know better, that whether there may be possibility of GW.
This is whether the dark matter halo itself has a sphericity to it? Is that an asphericity to it?
I'm saying that this maybe not be completely circular or something. It may be elliptical.
So it might not. The dark matter inside might not be perfectly spherical. In a lot of the parameter space we're talking about, you could actually compute that before it sort of forms a collapsing thermal structure. It might look something more like almost a collisionless halo, like what you'd expect in a galaxy. But then once it starts collapsing, it'll be at a kind of high temperature during that collapse. And so it actually should have more of a uniform density. It won't be perfectly spherical, I agree, just from random variations. But
okay, maybe we can talk later. Thank you.
Yeah, absolutely. Okay, I have gotten really wonderful questions, and so I will just mention that. So this is the bound on this sort of model that you can place, but there are some interesting signatures, if you will, or hints of this. There are all sorts of astrophysical anomalies we can find, because astrophysics is definitely an area of active exploration on just the standard model particle physics side. One thing my colleague Tim Linden and I looked at about a decade ago is that there is an interesting deficit of pulsars that have been searched for in the central 10 parsecs of the galaxy. And we looked at what dark matter model space would explain the absence of all the millisecond pulsars people have searched for there by saying, hey, they've turned into black holes, because of course at the center of the galaxy, the dark matter density is much higher. And so you can plot in terms of dark matter masses and cross sections what sort of the maximum age would be of neutron stars in the central region. Of course, we don't have much in the way of data for neutron stars in that central region. And so whether or not there are actually missing millisecond pulsars there, or whether just early estimates people made of how many they expected to find there, which now seem not quite to be correct, are just incorrect estimates to begin with is sort of an open question, but it's an interesting thing to think about, whether this could already be a hint of this kind of model. The converse of this is if you find a really old millisecond pulsar at the center of our galaxy, you'll have an exquisitely powerful and very stringent bound on asymmetric dark matter. And so that brings me to the end of dark matter and neutron stars. This, I should say, is a plot well, actually not this plot, but the refinement of this plot, which I should probably put here, was made by Ning Yang, but that's okay. Okay, so the last topic I'm going to talk about today is white dwarf explosions from asymmetric dark matter, and then I'll talk very briefly about connections to type 1a supernova and talk a little bit more about how we're looking at galactic structure as another way to probe this. I don't have a ton of time left, but that's actually okay, because we already know from our prior discussion and the great questions I was getting that, well, we know what we need in order to understand the dynamics of asymmetric dark matter inside white dwarfs. So first, I'm going to just review how white dwarfs explode. So a type 1a supernova, which is a white dwarf supernova explosion, occurs when some region inside a white dwarf is ignited, which is to say a thermonuclear reaction where carbon, oxygen, or carbon, oxygen, neon fusion processes take off and fuse the elements inside the white dwarf rapidly up to about half of the white dwarf gets to 56 nickel, and the other half gets to other heavier elements. So the whole thing explodes, and then over the course of about 100 days, maybe a little less depending on the supernova, what we see is a light curve, and this is powered by the 56 nickel decaying to 56 cobalt, decaying to 56 iron, and that's been flung out of the white dwarf. So when we think about dark matter and how it might cause a white dwarf to explode, one way is through dark matter core collapse, and that's a process I introduced and other authors have also written on over the years. And another way is you can just think about some really heavy dark matter state passing through and just heating up a small region enough that it causes it to explode. And this is something that was explored by other authors around the same time. And today I'm just going to talk about this process, partly because we've already talked about it with respect to neutron stars. So the process for the asymmetric dark matter to ignite the white dwarf will be actually the same process for it to make a black hole inside the neutron star, except in this case, it won't matter much whether or not it makes a black hole, because it will, in the process of collapsing, cause the white dwarf to initiate a thermonuclear explosion, meaning there won't be a white dwarf for any black hole to suck up or actually even collapse further inside of in the end. So in order to ignite a carbon oxygen white dwarf, the dark matter has to be heavy, again, so that it collects inside the white dwarf. It's the same set of equations as before. It'll end up in this small thermalized region. And then once it gets heavy enough, it collects to the point that it can collapse, but the energy it's shedding as it's collapsing, it turns out, is enough that it can heat to the interior of the white dwarf up to a temperature of an MeV, which is enough to ignite a type 1a explosion. A fun side note is that in this scenario, more massive white dwarfs would have dark matter collapsing inside them sooner, because those white dwarfs are more compact due to electron degeneracy pressure required to support them being much higher. They'll have a more relativistic electrons and be a more compact structure. And so the dark matter ball inside of them will also be contained in a smaller region, and the surrounding density will be higher. So they will explode sooner, and less massive white dwarfs will explode later. And so some work I did in 2015 just shows you what cross-section is required in order to get dark matter to collapse inside of a somewhat old, but not too old white dwarf, here for a temperature 10 to the 7 Kelvin, although this changes only a little bit for like 10 to the 6 and 10 to the 5 Kelvin, if you like that kind of temperature white dwarf better. And these sorts of coarse estimates have been refined over the years, and I'll show you a refinement in a second. Just to tell you for a moment about the ignition conditions, you can calculate what mass of white dwarf needs to be heated to what temperature, here shown on the y-axis. There's a nice, very thorough paper by Timms and Woosley from 1992 that's used to compute what temperature we need to heat the white dwarf up to. And then putting in that requirement in a very coarse way led me to these curves, which show you what cross-section you need for dark matter to ignite a 1.4 solar mass, 1.3 solar mass, and 1.1 and 0.9 solar mass white dwarf within either 5 billion years or a half billion years, shown here in blue and red lines for different dottings and dashings for different masses. And that can give you a type 1a supernova. Now, if you do these calculations with a bit more refinement, you get something that looks more like this. So it turns out that lots of additional processes can occur during the collapse and ignition of the dark matter inside the white dwarf. It turns out you can even have some parameter space where you Here, I'm showing you the bound from neutron star implosions against bounds from an old white dwarf in the Gaia white dwarf catalog that has not exploded. And as a result of not exploding, we can set this bound on dark matter shown here. Now, if you're of the persuasion that you want to think about, hey, what if type 1a supernova are being caused by this, and are there any interesting observations that might look like something that dark matter would be doing, then it turns out that there is an interesting thing to look at right now, which is that the actual way that type 1a explosions occur is actually not as well understood as you might think. So there is this review here, which you can go look at if you want, by Dan Maus, which goes over what's known as the type 1a progenitor problem. So a lot of the proposed scenarios for how you get type 1a supernovae don't quite mesh up with observational data. Here, what's being shown is that for some type 1a's that have been found, where we were able to get information on the light curve right before the explosion by just being pointed fortuitously in the right direction, we're not seeing the sorts of bumps or the sorts of light curve rise features that we'd expect if the white dwarf were in a binary system with a heavy companion. But probably the bigger interesting anomaly is that if you are told at some point in your astrophysics class that the reason that type 1a supernovae all look very similar is because they all come from Chandrasekhar mass white dwarfs, it turns out that there's, at this point, a lot of data that's come in that indicates that probably type 1a supernovae come from a variety of different mass white dwarfs. So here we have the mass inferred for the white dwarf as a function of ejected mass. And here we have the 56 nickel mass, which creates the light curve. And what's shown here is that a lot of the type 1a's that we're using, even when we do cosmology, for instance, probably came from white dwarfs that were lower mass than Chandrasekhar mass. That's okay, though. It doesn't have to be dark matter, by the way. You can think about white dwarfs merging and that giving you type 1a supernovae, or you can think about just piconuclear reactions, like interesting tunneling processes inside the white dwarf that aren't perfectly understood, that maybe could ignite the white dwarf spontaneously, even if it's just sitting by itself. But in any case, there's some interesting trends in the data where it looks like heavier white dwarfs might explode a little bit sooner than lighter white dwarfs. So that's something I looked into a while ago. And just to finish off my talk today and the time I have left, I'll talk to you about another thing I've been looking at. And that is the way that dark matter blowing up white dwarfs could show up in galactic structure. This is work I'm doing with my collaborators listed on this page here. Haifeng An, Javier Espedo, Gilda Victuchin, my grad student, Mark Richardson, and Lucy Sansom. So the idea here, if you've ever looked at galaxy modeling, is that there are sources of baryonic feedback in a typical galaxy model. So this is just in the standard model. If you go and look at galaxy modelers and you ask, how do galaxy modelers account for what's been seen, which is that dwarf galaxies have chord inner dark matter density profiles, which is say the dark matter density towards the center of many dwarf galaxies that have been measured doesn't look like an NFW profile. It looks like a dark matter profile that has a core inside of it. So how do galaxy modelers account for that in their simulations? Because they do see that in their simulations. The way they account for it is through something called baryonic feedback. And just to give you a very simple toy version of baryonic feedback, here's how it works. A bunch of gas cools down in the galaxy. That gas forms a bunch of stars. Some of those stars are supernovae. The supernovae go off. That causes the gas to expand. What this means is that the gravitational potential provided by the gas suddenly becomes very shallower very suddenly when all those supernovae explode. So if I think about a dark matter particle on some sort of orbit, it'll be on, some of them will be on a wide part of their orbit will be on a shallow part of their orbit even when this explosion takes place. And those will have the kinetic energy you expected them to get falling into the gravitational potential, but then they will have a much smaller gravitational potential suddenly. And so what'll happen is you'll get the particle ending up on a wider orbit after the blowout of the gas. And then so long as the gas collapses in a fashion that is not the exact same sort of reversible, that doesn't look like the process of blowout in exactly reverse, then you'll end up with some phase space of dark matter particles that end up on wider orbits. And this is the process of baryonic feedback causing dark matter density profiles to become flatter in the center of galaxies, because you essentially evacuate the center of the galaxy through this repeated process of flattening the potential and then causing it to get sharper again with the gas recollecting and forming stars, and then you start over again. All right, so what we've been looking at for the last 3 years, and when I say we, I mean Gilda, who's a very good grad student I've been working with, is what happens if you put dark matter-induced white dwarf supernovae into these galaxies? How do the features of the galaxies and this baryonic feedback story change in that case? And what we found is there are some, interesting differences. So dark matter baryonic feedback ends up being an interesting, very, very nonlinear, with nonlinears on top of nonlinearity sort of process, where it can turn off its own feedback, because as it's evacuating dark matter from the center of the galaxy, it's actually lengthening the time it takes for future white dwarfs to explode. So we actually expect dark matter-induced baryonic feedback to sort of shut itself off. What we found when we did simulations is actually a little more dramatic. We found that there is parameter space for dark matter at an intermediate cross-section, where it's creating white dwarfs at the center of the galaxy, which create a kind of baryonic feedback that cause a coring of the galactic structure. But it turns out that there's a nonlinearity to the size of this effect. So for an intermediate dark matter cross-section, we get a ton of coring. For a very low dark matter cross-section, we get something that looks just like if there were no sort of baryonic feedback from dark matter, which makes sense. But if I go to a very high dark matter cross-section, so I'm capturing it in the white dwarfs very, very quickly, I also get a profile that is less cored than my core collapse only feedback. And the reason for this is if I have the dark matter exploding the white dwarfs very early inside the dwarf galaxy, I will actually blow out the gas with so much energy that it will never come back in to form any more stars after that first epoch. And that means that core collapse supernovae won't go off. And so I'll actually get less feedback in total in that galaxy. And so it ends up being a somewhat interesting, non-trivial, non-linear process. And so we'll be coming out with a paper on this in the next few weeks. We have a final draft and we're just doing last checks on it at the moment. And so I think I'll leave it there and say I talked to you today about 3 ways dark matter can interact with compact stars. It can heat neutron stars either through infall or annihilation. And we can look for that in the future, hopefully, although there are many sort of astrophysical backgrounds and observational hurdles we'd have to overcome to do a really good measurement there. There's asymmetric dark matter causing neutron stars to implode. We can already set bounds using that process. And there are interesting connections we could look for astrophysical sort of signatures that already exist. And lastly, white dwarf explosions from asymmetric dark matter or composite dark matter causing heating inside the white dwarf and making it explode. And connections between that and type 1a supernovae and galactic structure. So thanks very much for your attention, and I'll leave it there.
Thanks for the nice talk. Very interesting. So if someone has a question, please feel free to ask.
I had a lot of questions during the during the
Hello?
talk itself, so.
Can you hear me?
Yeah.
I have a
Hi.
question about dark matter hitting neutron stars.
Yes.
For the highway dark matter, in this case, the dark matter will obtain the elastic energy to induce the inelastic scattering. Do
Yeah.
you think how much impact we have the inelastic scattering have for the dark matter hitting neutron stars?
Yeah, that's a great question. So, what about inelastic dark matter models, and what are sort of the limits on heating up the neutron stars? So I'm also finishing a project on this right now. There's a paper that's written, and we're finishing it off. So that's why I will have a lot of answers for you at this moment. So it turns out that if you think about dark matter being captured on neutron stars, you can ask, what is the largest inelastic mass splitting for the dark matter that can be excited by scattering with neutrons in the neutron star? And it turns out that the largest is around 300 MeV, or 0.3 GeV, which is very large relative to the sort of inelastic mass splittings we're sensitive to on Earth. Now, your next question was, how would this affect the heating? I think if you can cause this inelastic process to occur, and you're capturing the same flux of dark matter through that inelastic process, it shouldn't change the heating of the neutron star from kinetic energy being deposited in the neutron star, because you'll do that as you end up on tighter and tighter orbits around the neutron star. And so long as you're scattering with the interior of the neutron star, it doesn't actually matter so much which neutron in which area of the star you hit. It will heat up the neutron star nicely and uniformly. There's a really short thermalization time for neutrons with the neutrons around them after you hit them. So that shouldn't change too much of this heating signature. There's a separate signature we were looking for, and that we'll be putting on a paper on, and that is, can it take so long at the highest inelastic mass splittings for the dark matter to accumulate into the neutron star that the dark matter actually stays outside the neutron star long enough to annihilate there? And can you look for special signatures of that? And it turns out the answer to that is yes. But it's like a very special kind of dark matter that can do that. It has to be inelastic with a really large mass splitting, and it has to be actually quite heavy at present in order for you to see any discernible signals. Although there is one signal you can see, even if it's just as heavy as like 100 GeV or above. Yeah. So thanks.
Okay,
Did I answer your question? Okay. Yeah. Okay. Great. So then I see there's a question in the chat. They want to know more about how we implement the dark matter cross-section into the supernova feedback. I don't have a slide for that. I guess I could pull up the paper, but I won't do that. I'll just tell you really quick. So what we do is we're using a software package called Gizmo. So Gizmo is, I think, the state-of-the-art package for simulating galaxies, getting magnetohydrodynamic and all sorts of cooling processes right in galaxies. It's based on an older galaxy formation code called Gadget, and this is the code that people are using. If you've ever seen the FIRE collaboration in their galaxy simulations, they're using the same code. It's called Gizmo. So what we had to do with Gizmo is we had to write some new routines to keep track of star-forming particles. And then anytime stars formed in a star particle, or stars formed from a gas particle to a star particle, I should say, we populated them with a faithful number of white dwarfs, or really white dwarf progenitors, that we then calculated how long it took for them to turn into red giants and then become white dwarfs. And then we would also calculate how long those white dwarfs in that star particle at that point in the halo with the dark matter density and dark matter velocity dispersion around it, how long that would take that white dwarf to accumulate enough dark matter to explode. And then we would cause it to explode, and we would use the same core collapse supernova code, which calculates the energy injected in the halo around it on the type 1a supernova, which is a little bit of a coarse estimate, but should get things approximately correct. So yeah, we'd be looking to, I think, improve a lot of these calculations moving forward, but that's the basic procedure for how we're modeling the white dwarf explosions in Gizmo. Great. Okay, another question. Thank you for the lecture. I have a question concerning the selection of the velocity distribution function during the calculation of the capture radius. Capture formula is insensitive to the phase-space distribution of the dark matter in the vicinity of the celestial object. Yes, a bit. Going beyond Maxwell-Boltzmann distribution, the change in the capture rate go up 100%. In addition, I'm aware that analytic velocity distributions can also be derived using the Eddington version method. I would appreciate your expert opinion on the necessity of choosing such an analytic distribution function. Yeah, so what dark matter velocity distribution you assume can definitely have quite a large impact, especially depending on which dark matter parameter space you're looking at when it comes to determining how much dark matter is captured. I think, you know, a factor of 2 or a factor of 200%, or I guess that's a factor of 3. That's definitely something you could find in varying your Maxwell-Boltzmann distribution. I don't have an answer for what's the exact correct distribution. I think what's required is, you know, do our best to continue to refine our understanding of those distributions using some of the methods you've mentioned. And then if you've set up either a dark matter experiment or some sort of astrophysical system that you're using as a dark matter experiment, it's probably best to consider a variety of models and how your conclusions on a dark matter search are influenced by those. But I think, it's important to do more studies on what those velocity distributions are, and then to sort of marginalize over them when you're concocting dark matter search or experimental results. Thanks for the question.
So is there any other question?
So I have one simple question. So you talk about the subhalo in your neutron star heating projects. So did you consider the gravitational stability when you do the calculations? Because the subhalo around the neutron stars may be not stable.
No, our models of these subhalos are very simple. We just treat them as constant density objects, and then you're just computing collisional and collisionless accretion from them onto the neutron stars. I didn't get into it, but you know, even for collisionless accretion, you can think about some parameter space where maybe you could see something in the future, or maybe you could luck out and see one of them passing through a neutron star. In terms of a real model that, you know, realizes the subhalo, then you would want to think about the gravitational stability of that and whether it's something that should collapse further or whether it really can just stay at that one radius. That's a very good question. Thanks.
Okay, thank you.
Concerning that, the subhalos, in the models you use, what is the rate for encounter a neutron star with the subhalo?
Yeah, so I didn't go into this plot, but here it is. So the time between encounters is shown here on the y-axis. So only look at the black lines. And then for a 100-kilometer subhalo radius, the time between encounters is essentially shown here. So it can be up to 10 billion years, so that's too long. And then it can be, you know, down to 10,000 years. And And then when you make a subhalo radius that's coincident with the collection radius of the star, then for the purposes of thinking about heating it up, you actually have the shortest time between encounters in a sense. And then it turns out that, you know, this time between encounters, if you think about a really small radius or really large radius, then because now you're thinking about either the subhalos being very rare, or the subhalos being like almost becoming particles themselves that encounter the neutron star, you end up getting the same answer, which is this black line here for time between encounters.
I see.
Yeah.
So I have another naive question. At the beginning of your talk, you said about the neutron star can be an accelerator for dark matter particles. What is the process involved there? I mean, how
it's just gravity. It's just
gravity.
The escape velocity at the surface is 0.7 times the speed of light, because neutron stars are like almost black holes. So, you know, the black hole will have the, you know, speed of light sort of event horizon. This one has, you know, is a bit shallower gravitational potential, but close. So it's 0.7 times the speed of light. Yeah.
And nothing to do with the magnetic fields and stuff with some small charge.
No, I don't need to think about the magnetic fields. Yeah, just gravity.
Okay. So is there any more question? Any other question?
Hi. So when you try to calculate neutron star dark matter interaction, then you need to consider density versus R profile of dark matter. And
so in the case of the neutron stars, we definitely thought a lot about that the sort of time for the neutron star or pulsar to get eaten up by the dark matter and form a black hole will depend will depend on a radial function of distance from the galactic center, since the dark matter will be denser at the galactic center than away from the galactic center, and so this will change the accretion rate. My current collaborator Li Jingxiao took this a step further and said, even for these pulsars that you're seeing out in the galactic halo, those will move around in the halo as they're collecting the dark matter. So let me model their collection as a function of time, since they might move a little bit in terms of radius. Now, what Li Jing found was that in the end, this can affect the accumulation rate by an order 1 factor. Not too much, like orders
maybe not here.
Dissimilar. Yeah, sorry, I had to switch off of my headphones because they died, but am I back now? Can you hear me?
Yeah, now we're good.
Yeah, so you can do a calculation to see that, you know, you have a small variation in what you expect to, you know, compared to the approximation of just saying, okay, that pulsar has been roughly at that radius its whole lifetime. But yes, that is an effect that can be accounted for.
So there is no definite profile for rho r inside the neutron star or something.
Oh, you're talking about the profile of dark matter inside the neutron star. Sorry, I didn't understand. So there is a definite profile. So there's this thermalized ball at the center we're talking about, but then there's the whole population of accumulated particles that are going inside. I think there'll be, I think it's somewhat easy to calculate that. So you can just take the thermalization time and invert it, and from that get what the density profile is, since the thermalization time will essentially be like inversely proportional at a fixed radius to what the density of particles should be roughly hanging around at that radius. I haven't done that and looked at what that profile looks like, but yeah, that should be doable. Yeah.
Okay. And when you calculate this dark matter neutron star population inside the galactic halo, what do you we do have some definite profile for that, or I mean, in those regions? Like I have
Sorry.
the profile for rho r for dark matter inside the galactic halo. But do
Right.
you-
So that's go ahead.
yeah, please.
Oh, so yeah, I first started answering that question, that rho r inside the galactic halo definitely can affect the accumulation rate. And so that can be something that we can leverage to think about dark matter at the center of the galaxy, causing neutron stars to implode much faster than outside the center of the galaxy.
Okay.
But it's also something that you could think about doing just a more detailed calculation of the accumulation rate of any pulsar that you see in the galactic halo. And so what you would do is you'd take that pulsar and compute what its orbit is around the galactic halo, and then essentially integrate over that orbit. And that's actually something that my colleague Li-Jing Shao did in the last year using pulsars, and he found a small change, but factors of 2 are important eventually, in what the accumulation rate was of a selection of pulsars that he looked at that were the kind of pulsars you would use to set these kinds of.
Okay. Thank you for nice talk. Yeah. Thank you.
Yeah, your next questions.
So I guess that maybe we're done today. Thanks again for the nice talk, and very interesting. And
Thanks for having me. Yeah.
so see you all
Thank you.
next time.
Great.
Thank you.
See you.
Thank you.
Bye.
Looking
Bye.
forward to see you somewhere.
Hey.
Yeah, I hope to see you all sometime soon. Yeah, bye.
Bye bye.
Bye-bye.